Hi guys, Mr. Johnny here. This video, Mess on a Bench, is the second revision of this inductively heated soldering iron. You can see there I redid the working coil. Working coil now contains 94 turns, around 8mm former, which happens to be the diameter of this handle of this hobby knife. So I went and used an 8mm ID fiberglass tubing, just shoved it on there, then wound 94 turns in two layers. Then I fixed that wire with a Kapton tape, and it seems to be alright. But the problem is that the tubing I used is this one. You can see there. And the problem is that you may be able to see how shiny it is, right? You see that it's not just a fiberglass, it is soaked in something. And that something, unfortunately, is not as thermally stable as I want it to be. Long story short, it smokes. If the tip goes hot, it smokes quite a lot, and that's kinda inconvenient. First it smoked a lot, now it calmed down a bit because it burned out, obviously. So yeah, now it works quite good. The controller now is same kinda deal comparator, but the chip there is OP07, and now it's performing really well. The disadvantage of that chip though is it cannot sense from ground, so I have to add a negative rail there, which is this battery. The negative rail does not have to be even regulated. You can make it like 1.5. You can add like 3 volts there, negative rail, and it will be fine. It doesn't have to be equal to the positive rail. It just has to be a bit below the ground, so the op-amp will reliably sense the little voltage produced by the thermocouple. Negative end of the thermocouple is reference to the real ground, so that's why you need an op-amp to sense from that point. Alright, now I tested it. It seems to hold the temperature extremely well, if you ask me. Considering that that's just a comparator, it is pretty good. Because right now it's about 320 degrees, and it turns off at 322. Well, it actually turns off at 320 and turns on back again at 318, which is fantastic. Why? But there is some overshoot, so the temperature just fluctuates between 318 322, but that's still awesome. Let me show you that. Power it up. Focus on it. Alright. I'm gonna try to hold it there. Wait, that's something fishy. Ah, damn it, the thermocouple just bent. Let me fix it. Here we go. Very inconvenient, but we gotta do what we have. I'm gonna put this so you can see the LED there, which comes on and off. See? It doesn't allow the temperature to go much. It just stays there between 322 and 327. Of course there is some overshoot, but god damn it, I mean, like, considering what it is. Considering what it is actually, the performance is fantastic. Ah, the thermocouple is sliding away. It's very flimsy thermocouple, that's what it is. Anyway. So you saw the temperature is not very high. I'll give you some demo. The tip is oxidized a little bit, but as you can see there, not a big deal though. Just like that. And we're molding. And if you look at the LEDs there, when it's idling, you see it's quite short. But if I'm gonna load it up by touching this polygon, this blob will do, you will see that it takes longer for the LED to go off, and it comes on more often. Long story short, the feedback is working pretty good. Yeah, what can I say? It just works, as you can see. It's a lead-free solder here, by the way. Easy. The heating up time is about 11 to 12 seconds. It's melting solder, and about 35 seconds now to reach the preset, which is 310 degrees. Around about that, so it's pretty good. Now I'm gonna show you the schematic. So now, as promised, the schematic, which is this. Very simple. Let's start from left to right. Here we have our thermocouple in the tip, which is fed into this RC filter that is there to make sure that the noise coupled onto the wires going to the thermocouple won't affect the operation of the comparator, because the cable contains 5 wires, one for ground to ground the actual tip, 2 for the heater, well, was for the heater, now it's for work coil, and 2 for the thermocouple. So they're running just adjacent to each other, like that. So there will be some capacitive and inductive coupling between them, and the power to the heater, the power to the work coil, excuse me, is a sine wave, but it's an AC nonetheless, high frequency AC, so it will get coupled. Like this. Alright. Let's proceed. Next we have this potentiometer there, 1K pot, 330K limiting resistor, which is there to make sure that the voltage here is just about like 12 to 15 millivolts. I forgot the figure. Basically what it is, to make sure that the maximum voltage you can choose here on this potentiometer is gonna be in order of tens of millivolts. And that is the voltage that the thermocouple produces at its desired temperature. So the maximum temperature you want, like 380 degrees or 400 degrees, whatever. Measure the temperature and put a limiting resistor of such value that right here, when the wiper is in the uppermost position, you will get that voltage. There is some 82 nano capacitor there, just to make sure that this node of the circuit is also RF quiet. You don't have to use 82 nanofarads, obviously. You can use 100 nanofarads. The reason I'm using 82 nanofarads here and there is purely because I was shopping and 82 nanofarads were cheaper than 100 nanofarads, so that's what I got them. I'm a cheap ass, what can you do? Anyway, you can see the comparator. It's a OP07 op-amp. It's advertised as ultra low offset voltage, and it is quite nice. The version I got is OP07C, which has a maximum input offset voltage of 150 microvolts, which is 0.15 millivolts. And the thermocouple produces about 12 millivolts when heated to about 300-ish degrees. So we are fine there, because the offset is a fraction of a small fraction of the voltage produced by the thermocouple. That's why you saw that the hysteresis improved a lot. The temperature was held in much tighter band. This is just some indicator to let you know when the heater is on, if you will. Some decoupling there, RC, because ZVS may put some noise on the supply rail, so I decided to decouple the power supply for the chip. And this op-amp is different from 112904 because first, it's an ultra low offset voltage op-amp, which is nice, what we need here, but unfortunately this op-amp cannot sense signals from ground. To put it to say it in a scientific way, this op-amp, the input common mode voltage range of the inputs on this op-amp do not include negative rail. That means if you want the input to sense the voltages which are close to the real ground, you have to put some negative voltage on the negative rail of the op-amp. 3 volts is more than sufficient. You can use higher, as you saw in previous chunk of the video. You saw me using 9 volt battery because that's what I had laying around and it's convenient. You can also use 9 volts, but you can get away with only 3 volts. Which you may actually get by putting a little bit, by creating a very simple charge pump circuit. This capacitor, 470 picofarads, is there to ensure that the output transition is clean. It won't jitter, it will just turn on or turn off. It won't just like jitter uncontrollably, because as you saw from the LED there, from this LED or from the LED on the board, it is quite nice. It just on, off. Very clean switching. Then that signal is fed to this transistor, which turns on this transistor, and when this transistor is on, it connects this node of the circuit to the positive rail, thus starting up the oscillation of the ZVS. ZVS is made using classical schematic, center tapped coil, nothing fancy. The ferrite I use there is, again, it's a little ferrite, it's a ferrite filter from a VGA cable. You may see a thickened section on a VGA cable near the actual VGA plug. That thickened section is nothing else than this ferrite, which is there to filter out some noise picked up by the wires. So the primary is 12 turns center tapped, 6 turns in each half. The resonant capacitance I'm using is about 220 nanofarads. I'm using two 100 nanofarad capacitors. Not critical. It just affects operating frequency. You obviously want the frequency to be reasonably high, but not unnecessarily high. Ideally, I suggest you to set it about 30 kHz, 30-40 kHz, more than sufficient. You don't want it to be in audible region, so the thing won't squeal. Mine is actually just on a brim in audible region, so that's why you may hear it whining. Another thing that whines here is this power supply, which you can see on there. It's a modified ATX power supply, and I did a poor job doing proper frequency compensation there. So it actually has a weird oscillation, has instability problem. The thing is that this uses TL494, which is a voltage mode PWM controller, and making a loop compensation, doing loop compensation for voltage mode controllers is a bit more tricky than it is for current mode controllers. Alright, so else is a typical ZVS, as I mentioned. Secondary 17 turns, goes through the cable to a work coil, which is 94 turns on 8mm former. You can do a little bit tighter radius diameter. I decided to use 8mm because it's convenient, and that happens to be the dimension of this handle on the hobby knife. And I also bought that fiberglass tubing in hope that it will be thermally resistant, but it's not. The actual fiberglass is obviously pretty much fire resistant. It doesn't care about soldering type temperatures, but the thing is that it's soaked with some compound, and that compound literally stinks. It smokes vigorously and it stinks. Right now it doesn't smoke that bad because it burned out. Alright, so MOSFETs I used IRF3710. Why? Because I had them. You can use anything pretty much here. Typical choice would be IRF-Z44. It will do just fine. When powered from 15 volts maximum, they will do just fine. Yeah, that's typical stuff. Again, you may wonder why why so tricky? Why not to connect the output directly to this node? Well, first off, this is not a rail-to-rail op-amp, so its output cannot swing to the positive rail, neither it can swing to its negative rail. So, swinging to the negative rail is actually not a big deal here, because the emitter of this transistor is referenced to real ground, and the negative rail of the op-amp is referenced to the negative supply. So this transistor will be properly off. But the problem is that I want the output to be really high, preferably to swing all the way to 12 volts, and that won't be the case using just the output like that. If I connect it like this, just use a PNP transistor through the just here. This transistor will never switch off, because again, the output cannot swing all the way to the positive rail, and the emitter is in positive rail, so in order to shut this transistor off, the output of the op-amp has to swing at least 500 millivolts shy of the positive rail, and unfortunately it cannot do that. That's why you see this transistor there, because when this transistor is open, the circuit is like this. The transistor is kept closed by this little resistor, which makes sure that there are no strays can go and turn on this switch. 12 minutes. Alright, I'm gonna leave it here. Obviously, if you have any questions, leave them in the comments below. That's that. Thanks for watching. See ya.